that starch is a plant product. Turns out we've got the same deal in our cells, at least some of our cells. But because we're better than plants, we can't call our stuff starch. It's glycogen, but it's essentially amylopectin. The only difference is that it's slightly more branched. The branching happens every 8 or so instead of every 10 to 20. So a little bit more branched. This makes a good way to store glucose in any cell, whether you're talking about a plant or an animal cell. It keeps them from diffusing out the glucose molecules. I think we talked about this last time. They're prone to leakage out of cells. You can phosphorylate them to trap them inside, or if you link them up with these big starch molecules, they can't escape that way. So it's one way to store them without loss. It also helps tremendously with the osmotic strength situation. If you had 100,000 glucose molecules, you'd have a very high osmotic strength because it's related to the number of molecules. The cells would probably soak up water till they burst if it wasn't for the...
So phosphate, and what else keeps the glucose inside?
Making starch molecules.
Oh, making starch.
This guy isn't going to escape through a membrane. A little single glucose molecule by itself is small enough that you can make it leak through the membrane.
Oh, okay.
But if you tie it up into a giant macromolecule, it's locked up inside. So that's what amylopectin or glycogen might look like, where each one of these is a glucose molecule. Actually, we won't get into the details of it, but in the core of these starch particles are actually little protein molecules. It doesn't start with a single glucose, it starts with a glucose attached to a protein, and then an enzyme kind of is centered right in that area and starts building out. Okay, why branch? Why have branched versus unbranched carbohydrate? The amylose, the unbranched one, is a little bit longer term storage, even though you consider this long-term storage. This is a little bit more easier to work with for cells who need energy more rapidly. So when we store this in our liver, when we store this in our muscle cells, there are times when the body says, break down your starch reserves, give me some of these monomeric glucose molecules. That's one of the main jobs of the liver, right? To maintain a constant level of glucose in the blood. If you haven't eaten all day long, glucose levels are dropping in the blood. Hormonal signals will go to the liver and say, break down starch, which we call glycogen in the liver, and send out some of those free glucose molecules in the blood. Okay? A muscle cell, the same deal. If you're storing this as a backup energy reserve in your muscles and you start sprinting, all the metabolism ramps up. You want ATP, which means you want to break down glucose molecules, which means you need access to lots of glucose very rapidly. Imagine if you had just one giant amylose molecule in your muscle cell. The way the breakdown happens is you attack the non-reducing end. So let's say here we have this long amylose molecule, and you're asking the muscle cell to work real hard. It wants to get some of this fuel and start processing it. There's an enzyme that will come in and hydrolyze this, give you free glucose. Then it moves on to this one, gives you free glucose. If you have just a giant, long amylose molecule, it may have 100,000 glucose units in it, but it's only got one business end,